Good morning, class. We'll end Chapter 7 with Section 7.3, the central limit theorem with proportions. How often have you heard that some percentage of the population would do this or favor that? Have you ever wondered how researchers come up with these figures? We're now in a position to explain perhaps the most commonly encountered use of statistics. Proportions. A population proportion, denoted by P, is the percentage or fraction of the population that has a certain characteristic. In a similar manner, a sample proportion, we denote by P hat, which is read P hat, is the percentage or fraction of a sample that has a certain characteristic. In other words, a proportion is the relationship of one part to the whole, whether it be a sample or population. A population proportion is given by P equals X over capital N, where X is the number of individuals in the population that have a certain characteristic, and capital N represents the size of the population. A sample proportion is denoted very similar. It's X over lowercase n, where X is the number of individuals in the sample, this should read sample, not population, that have a certain characteristic, and n is the size of the sample. Let's look at an example. If a census shows that 9 out of every 10 people carry a cell phone, then the population proportion is 9 over 10, or 0.90. Or we can represent it as 90%, as this is more easily understood by the majority of people. If we ask a sample of 20 people if they carry a cell phone, and 16 of them say yes, then the sample proportion is given by P hat equals 0.80. Or what we would tell people as 80%, as this is more easily understood by the majority of people. Some background. A sampling distribution of sample proportions has a binomial distribution, not a normal distribution. However, from section 6.5, we can use a normal distribution to approximate a binomial distribution when the following conditions are met. So we require n times p to be bigger than or equal to 10, and n times 1 minus p to be bigger than or equal to 10. This ensures that the histogram, or our bar graph, is symmetric and can be approximated by a bell-shaped curve. What the histogram looks like when the conditions are not met are the following. Here, notice that both binomial distributions are not symmetric and cannot be approximated by a bell-shaped curve. Notice if we even tried to put a bell-shaped curve around it, it just doesn't look correct. However, when the conditions are met, we see that the distribution can be nicely approximated by a normal curve. It looks very symmetric, and now it represents our normal curve. First, we need to know how to change the standard score formula in order to use it when the conditions are met. To do this, let's first recall the values of the mean and standard deviation for a sampling distribution of sample proportions. So it turns out that our mean of our sampling distribution of sample proportions, we denote this by mu of p hat, is our proportion. It's our p. We can think of this as our binomial probability. And our sigma of p hat, our standard deviation of the distribution of sample proportions, is given by this nasty square root, the square root of p times 1 minus p divided by n. Furthermore, we're looking at values of the sample proportion, again another typo, I'm sorry about that, sample proportion p hat, not specific values of the random variable x. Remember that the standard score formulas are always created as follows. We always take our data value minus our mean divided by our standard deviation. Remember from chapter 6, this looked like x minus mu over sigma. But now we're going to look at our p-hat distribution. So our values on the number line are going to represent p-hat values. So we're going to take p-hat minus the mean of my distribution divided by the standard deviation of my distribution. So I have p-hat minus p over the square root of p times 1 minus p over n. Now, on your exam formula sheet, you're only given this formula. But if we remember this idea that we always subtract the mean of the distribution and the standard deviation of the distribution, we can easily see that on our formula sheet. This is mu of p hat, and this is sigma of p hat. So keep that in mind. That might show up on your next exam. Let's look at an example. In a certain conservative precinct, 79% of the voters are registered Republicans. What is the probability that in a random sample of 100 voters from this precinct, at least 68% of the voters would be registered Republicans? To solve this problem, we need to appropriately label all values given in the statement of the problem. We know the sample size is n equals 100. Since we are dealing with percentages, we can use our sampling distribution of sample proportions. We are asked to find the probability about a percentage of the sample. So, i.e., we are asked about a p-hat value. Some mathematical equivalence, remember that at least can be written as our greater than or equal to, at most can be written as our less than or equal to. You may have seen these words in some previous sections, but let's remind ourselves that at least is equivalent to this statement and at most is equivalent to this statement. Using this fact, we are asked to find the following, that at least 68% are registered Republicans. So p-hat is at least 0.68. Remember, we never use percentages in mathematical statements. We always write them as decimal numbers. So recall that this represents the area to the right of the value 0.68. We can use two methods. So our first method, if you prefer using our statistical tables. So we first standardize our value, p-hat is 0.68, and we do that using our formula given on our formula sheet. So 0.68 minus 0.79 divided by this square root. So recall from the problem that they give us the p. Remember, going back to section 5.2, when you're given a problem with a fixed percentage, you should think, oh, this might be a binomial. This is our binomial probability. In a certain conservative precinct, we know 79% of the voters are registered Republicans. This is our p-value. So this will help us in this calculation. So we get z is negative 2.70. Next, since we want to find the probability that at least 68% of the voters would be registered Republican, we use table A, since the value is negative, along with our complement rule. Remember that area to the right is 1 minus the area to the left. So we look up the value and get the area to the left, and to find the area to the right, we take 1 minus that value. Now, if we use our graphing calculator, we can do this calculation directly. And again, please review your step-by-step guide found in our Canvas course. So now we want to use our normal CDF, and since it's an area to the right, we're starting at the value 0.68, And our right endpoint is going to be 1 times 10 to the 99th. So remember, this is our notation for using our scientific notation. Our mu is 0.79. Remember, our mu is p. And then our sigma is this nasty square root. And we hit enter, and we get 0.9965, which is exactly what we got in our last problem. Now, this chapter is very different and may cause some struggles for some of you students. If that's the case, please reach out to me. I have a handout that explains the different types of distributions we've discussed: our z distribution, x distribution, our x bar distribution, and our p hat distribution, and the qualities that it has. So please review that before reaching out to me. But if you're still confused, please reach out to me, whether it's a post in the discussion board or an email directly to me. If you need to schedule a Microsoft Teams meeting, we can do that as well before this next exam. This is one of the hardest exams for students, so please take your time, study, and make sure that you're reading the problems extremely carefully.